In this video, I'm working on the upper control arm design and the bump stop design for the Ultra4. I'm starting with this Piggyback bump stop from King. It's a really cool product that they came out with recently. I haven't seen it on too many cars, but I've seen it on a few, and it's a really cool design because it's basically like a piggyback bypass shock in the form of a bump stop, and it's a 3-inch diameter with I think it's a 9-inch stroke, so it's a really cool design. So what I need to figure out is where this bump stop is going to interface with the lower control arm. I think what I'm probably going to end up doing is a slapper arm where the bottom part of the bump stop is attached to its own little arm that interfaces with the lower control arm. I've seen a design like that from Camberg Racing on some of their Raptor long travel kits, and from Morgan Clark Design. He has these really cool, he calls them slapper arms. That's going to come in a later video. But for now, what I'm doing is I'm building the assembly so that I can cycle this shock. I'm using a new type of mate here that I've never used before. It's called a limit mate. So it basically constrains the movement of a part within an assembly with a maximum and minimum distance between two reference points. So it's perfect for shocks because it allows the piston of the shock to cycle through the cylinder of the shock within a limit. So again, following best practices here, you want at full compression, you want the axis of the shock to be perpendicular to the plane of the lower control arm. So setting up that angle here, maximum compression, I need this shock to be 25 degrees in relation to that plane. So basically, I'm just checking to see how much room I have on the front part of this lower control arm and adding the spherical bearing mate to attach the top part of the bump stop to. Typically, these bump stops are mounted inside of a chromoly tube, and then they just bounce off of the top of the knuckle. But since we're doing the tall knuckle design on this, it doesn't really make sense to put it way up there because it'd be above the driver's head. So I'm going to have it bounce off of the lower control arm somewhere where there's lots of room. But what I come to realize during this design process is that I have a lot of interferences on the lower control arm, and I need to redesign it. You can see here that the tall knuckle interferes with the shocks. So I started by just switching the location of the coil carrier and the piggyback bypass shock, because that'll give me a little bit more room. But what I end up realizing is that the tire itself is going to crash into the bulk of the meat of the lower control arm. So rather than having this asymmetric design, I need to make it symmetrical around that plane defined by the axle, and I need to reduce the steering angle. So the goal for the steering angle was plus or minus 30 degrees. I think plus or minus 25 is more realistic for this, and I think that's plenty. This isn't like a drift car where you need 45 or 60 degrees of steering angle. I think for an off-road and rock crawling application, getting as close as possible to 30 degrees is going to be just fine. So the great thing about this particular design of the lower control arm was that I have all of my complicated features referenced off of planes rather than referenced off of each other. So what I can do is just adjust the location of those planes like I'm doing right here, and then everything will end up in the correct place. So following that process again of rolling the feature manager back and then readjusting each feature one by one so that I can get everything moved without blowing up the whole part. So these are these pocket cutouts for the shocks, and making sure that I have all the radiuses correct on the internal fillets for those ball end mill operations. That's super crucial. This ended up being a little bit trickier the second time around. I'm not really sure why, but I ended up ultimately figuring out how to get all of these features in the place that I need them to be. So I'm adjusting the hardware locations. It ended up being better having the shocks straddle the axle because it allows the bolts to insert into the assembly from the outside, which reduces the number of cuts that I need to make on the lower control arm, which makes it stronger. And so just adjusting these shock locations here, realizing that I have some sort of a strange offset on the lower control arm. So now that I have features in the assembly that I can mate to, I no longer have to be sort of counting inches and adjusting plane mates. I can adjust part locations and feature locations in a way that makes more sense. So I need to move the shock mounts in a little bit. They were right at the midpoint of the part between the bushing mount locations and the spherical bearing locations. They need to be moved in quite significantly, but that's okay because it just decreases the lever arm on the shock So you need a slightly higher spring rate, but you need slightly less stroke on the shock, which is no big deal. I mean, spring rate can be basically whatever you need it to be. And then stroke for a King shock like this would probably be a custom specified shock that you would send the dimension requirements to King and they would make it. So the part's starting to look a lot better now. Now I just need to add some more cuts. So I'm making a little sketch here to represent the wheel and then figuring out which cuts to make sure everything fits properly. And these cuts ended up being pretty simple, pretty machinable, and right in the right spot where they're not going to compromise the structure. I was anticipating cuts like this, so this ended up working out pretty well. Hopefully I don't have to rebuild this entire part. The only thing I'm worried about is that narrow piece at the end where the spherical bearing attaches. It looks pretty thin to my eye, but it's still 2 inches thick and 4 inches wide. I think just by virtue of the fact that this part is gigantic, it looks small in relation to everything else, but it's still going to be plenty of meat, plenty of aluminum to have the strength that I need. So that's what I'm working through here. So again, just going through and checking all my interferences as the part cycles through. I realized that there was axle binding because the axle location on this tall knuckle was a little bit too far inboard. So as the part cycles through the suspension geometry, the distance of the axle increases and decreases a little bit too significantly. So I need to move that axle mount inboard a little bit and make sure that I still have room for those drafted cuts for the axle clearance. And that looks a lot better right there. So what I'm doing now is bringing in the upper control arm design from the previous revision of this assembly and start using that to adjust the dimensions of it and make the design work within the context of the new suspension angles. So I need to reduce the width of this upper control arm significantly, and I need to make sure that I retain all the same feature clearances so that it can cycle through without hitting the tall knuckle. So trying to figure out what those reference dimensions need to be by way of a sketch and then adjusting it in a way that makes sense. So the great thing about this design is that it uses rod ends as pivot points on the inboard side and spherical bearing on the outboard side. And the reason for that is if you want camber and caster adjustment, you can do that by threading in and out those rod ends, which will adjust the location of, it'll adjust the alignment of the wheel with respect to the chassis. And those are the biggest rod ends that I could find on McMaster. They're 2-inch ID. That way I can use matching hardware and matching misalignment spacers on those rod ends, the same as I have on the spherical bearings, which is really nice. So the dimensions of this part need to change significantly. I want it to be sort of a tabletop shape rather than a V shape because it's going to look a lot more normal when the car is at ride height. Right now it looks kind of goofy with that big point sticking up in the air. So I'm seeing where those cuts need to be and realizing that this part is probably way thicker than it needs to be. But it was nice to start with this part that has all the cuts and clearances already in there. Then I can just adjust the dimensions around that. So with the suspension at full compression, I toyed around with the idea of just making the upper control arm a flat part and then having big cutouts in the middle. But I think it looks cooler the way that I had it originally. And the reason for that is this whole design process is basically a design study around what would happen if you rebuilt the Can-Am Maverick R suspension around 58-inch Mickey Thompson tires. So those side-by-sides are incredibly well designed in terms of suspension. In fact, one of the Can-Am Maverick R's just won the King of the Hammers Ultra4 race. And it didn't just win the UTV class, it won the whole event. So it's a really great design. This design study is like, what would happen if you scaled that suspension geometry up by a factor of about 2? So rather than 30-inch tires on a UTV with a little tiny engine, what if you had 58-inch tires on an Ultra4 with a big block? That's what I'm trying to figure out here. So yeah, now just adjusting some of these features. Now that I have the profile of the upper control arm the way that I want it, I just need to make those clearance cuts in a way that makes sense so that I need to do 3 things. I need to capture the spherical bearing, capture the rod ends, and put clearances in for the tall knuckle to cycle through in steering. So these radius cuts on the outside are just to make the part look cool in its envelope. And then the interior cuts on the inside are to capture the heims and have clearance cuts for the tall knuckle. So reducing the overall width of the part, because the original one was way bigger than it needed to be, since my new steering angle will be plus or minus 25 degrees. And this part is close to being done, just adjusting some features here. Now that the profile and the envelope is set, now I can just design the internal features to capture the hardware and make sure all those clearances are where I need them. This cut in the middle is to clear the tall knuckle. You can see I have that 45-degree angle in there for steering, which is way too much. Plus or minus 45 degrees that's like drift car spec. So way too big. It took me a while before I noticed that, but I ended up reducing that 45-degree angle down to about 30 or 35. And checking the cycling here. So the constraint on the steering is defined by the misalignment spacer on the spherical bearing. So if I have a 25-degree maximum misalignment on the spherical bearing, that sets my angle for steering. So that made the part a lot narrower in width and made these cuts a lot simpler. So I'm happy that I'm able to keep a lot of meat on those arms for strength and still have plenty of clearance for cycling at full compression, where the tall knuckle is going to run into the upper control arm. So what I'm doing here is trying to get the mates correct in the assembly. SolidWorks was a little bit confused by the spherical bearing placement that I have, because they're at strange angles with respect to each other, both in X and in Y. And so what I like to do is fix the spherical bearings in place and then attach the moving parts to them by way of a point mate, not an origin mate, because when you do an origin mate, it aligns the axes by default. But the point mate is always unconstrained except for that point. So it allows everything to move in the direction that you need it to for a spherical bearing to work. So now I get to do the fun part of this upper control arm design, which is put in all the lightweighting cuts. So before I do that, I just need to fix some hardware locations. I ended up getting rid of that center heim because it's unnecessary. I just need 3 points of contact to constrain the part in space. And I need to make some clearances here for the spherical bearing hardware. And then I'm using the exact same hardware on the lower control arm as I do on the upper control arm. So that includes the spherical bearings, the misalignment spacers, those heat-treated inserts, and the 1-inch grade 8 bolt and castle nut. That just makes the whole assembly a lot easier because you're using the same hardware spec everywhere, which is really nice. Fixing some more mates here so that everything lines up properly. What I ended up doing on this one was aligning an axis of the upper control arm assembly in the upper assembly rather than fixing those spherical bearings in place, because these mates were just either breaking each other or leaving the part over constrained. But I ended up figuring out a better way to do that. So now that I have everything mated the way that I need it in the upper assembly, I can start designing in some machining features. So that means putting radiuses on all the inside corners and then working in the lightweighting cuts on the exterior of the part. This is my favorite part of the process because it makes the part look done, which is exciting. It also disincentivizes you from overworking it and making the part more complicated than it needs to be. Starting by chamfers on the exterior corners and then designing in some pocket cuts on the top. So this turns the flat part of the upper control arm into like an I-beam profile, and then adding some drafts so that it'll be ball and mill operations and there's no interferences between the cuts, no thin features between the cuts. And it just makes it look really cool.